Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
With the irregular curve shape, we're only getting an approximate area, we're only getting an estimate. We can use any shapes we like. The more shapes we use, the more accurate our answer will be. And then we try and pick a shape that is kind of effective and efficient, and that was the trapezium. So looking at that now to see where we take it from there, we have broken up our shape into a whole load of regular trapezia, and we're going to try and find the areas. So there's the first trapezium. Now I think if I was explaining this, I'd put an x-axis and a y-axis on the shape. Because, right, to find the area of this first trapezium, what are we doing? We have to get this height and add it to this height. In the exercise you were doing, we were measuring this. But like, tell me another way we could say what that height is. If it's up along a y-axis, what is it really? It's a y value. What y value is it? It's the first y value. So it makes sense to call it y1. And that's notation that leaving certs have from junior certs, so there's nothing new or mystical about that. Logically then this is going to be what? The y2, and we're adding those together, multiplying by the distance between them and halving it, so there's the first trapezium. And basically we're repeating that, so for the next trapezium, what's this going to be? y2, and this will make sense to be. Now in a sense, with this, I'm already making a connection because the trapezoidal rule is strand 3 material. But I'm actually connecting this up with functions now because we're gone to a function. We're talking about its y values, its heights. So there's already even a cross-strand link being made there. And so on for each successive trapezium until we get pretty much towards the end. How many trapeziums have we? We could have any number we like. So let's say that this last height is the nth height. Now careful, it's the n-1th trapezium. But because of the two values, this is the nth value. So you're going to have yn minus 1 plus yn by the h, half it. So that's how we calculate the area, which is quite cumbersome. So can we do anything to maybe tidy it up? And if you like, slightly another link, let's go do algebra. What can we do with all of that? And take out the h. So the half and the h are out. And what are we left now inside in the bracket? And start looking at it. How many times have you the y1, the yn? But what about all the rest? So we could write it as h over 2, y1 plus yn twice y2 plus y3 yn minus 1. Now, who's going to spot the deliberate mistake on the board? What did we learn? What was the first thing we learned about the trapezoid, about this activity? It's only an estimate. It's not equal. That's wrong. I don't know, should I be putting wrong stuff up on the board? But I really want to drive home the point that it's So actually what it should be is A is approximately equal to. All right? So it's only an approximate, and as I say, a lot of students, once they fill into a formula, they just have this thing in their head, sure, that's a formula, that has to be perfect, gospel. Now, that formula is in the logbook. Some teachers I know make them learn it off by heart. And they have things like h over 2, the first one plus the last one plus twice all the rest. Why would you be making students learn something off by heart that's inside in a logbook? Now, the answer you get to that question sometimes is, for God's sake, Tony, those Y1s and those YN stuff, and nobody could be expected to know what that means. But simply by sticking the y-axis on the thing originally, when you were deriving the formula, it lets them see that notation actually means something, and it's a notation that they have used right throughout first, second and third year. So it's not new, it's not mystical, and surely to God, if it's in the formula in the logbook, we should be able to explain it. And okay, like, yeah, that's the first height, that is the last height, that is the height that is 1 from last. Yeah, of course we have to explain that. So we've got the formula, we know it's an approximate. I think the next thing to do now would be everybody gets their shape and they have to go and find the area of it again on the other side using trapezoidal rule. And what you will definitely see when you start putting them back together again, this time your degree of accuracy is going to be much increased, pretty much across the board. They have to practice this. There's the question of the sample paper for 2012. They got the shape, they got no lines whatsoever drawn, nothing, just literally calculate the area under the shape. So they have to have more than just a formula to fill in. They need to know what? You know, they're drawing the vertical lines, they've got to space them the same distance apart. They have to be able to physically do the measuring. Measurement skill is now very important in the syllabus, and maybe they didn't do a lot of it in the past. This has replaced Simpsons rule. So all of the old things that used to happen with Simpsons rule can still happen with this. Like, for example, the first height might be 0. The last height could even be 0. Do you know, would it even be a stretch to say one of the heights in between could even be 0? If it's 0, it's 0. The y value is 0. Big deal. But why has it replaced Simpsons rule is a question I kind of thought of asking myself. Has anybody here actually taught Simpsons rule? So I'll tell you, I'll get one of you to come up to the board and derive the formula for Simpsons rule. Can you? Now, I couldn't until I started preparing for this workshop. I didn't even know what it was based on. What is it based on? It's actually based on finding area under little quadratic curves. Nothing to do with the syllabus. It's very difficult maths as well. So we were using something that we didn't even know what it was about, and we weren't able to derive it. We've replaced it with something, the basic shape for which the trapezium is on the syllabus. It's much, much easier to derive and to kind of see what was going on because you were working with straight line shapes. And in practice, it's more efficient because it's simpler to use. And degree of accuracy we don't have to worry about because this student brought the issue up ages ago. We can get any degree of accuracy with any shape on condition that we take, and enough of them. And they're the kind of discussions and comments that you want coming out of these activities within the class so that the students are seeing it. Now here's an interesting question. It was on 2001 ordinary level paper. So it's old syllabus if you like. So it says, hence use Simpsons rule. Well, clearly that has to be changed now to use the trapezoidal rule, okay? But the same question could be asked. And if you think a step further, you could even take all that away and just leave the question, estimate the area between the curve and the x-axis. What's the insert tool for estimating area? Trapezoidal rule. But now, how do you find the heights? You're not measuring. Why? They're given a y value. So how do you get the y values? It's a function. You fill into the formula, but you have the link back again, and you're connecting strand 5 with strand 3, and the way we sort of derive the formula hopefully makes it a bit more obvious that to find the lengths there, we just fill in, which I did, and on the assumption that I can do maths some bit anyway, I actually worked out the answer, and I got an answer of 26. But now the question I want to ask: which one of the following could be the exact area? 25 1/3, 26, 26 2/3. Which one of those could be the accurate area underneath that curve? First one. So could 26 be the right answer? Why not?
It's an estimate.
Yeah, 26 is gone anyway. Because what? It's an estimate. But for that curve is what we're talking about. What were you doing?
It's the straight of the curve. It's a...
Now, what is going on behind the scenes when you do the trapezoidal rule? What do you do when you fill into the trapezoidal rule formula? What are you really doing? You're finding the area of trapeziums. So let's have a look at the trapeziums. There they are. Agree? And it was on the basis of that I got my approximate for 26. And let's look at the real area now. The real area under the curve. Oh. What about all of the trapezia? They're all sticking their heads up above the parapet. All of the trapezia, every single one of them, are overestimating. So the overall must be too big. The overall trapezia must be an answer that's too big. 26 is an estimate, definitely, and it's too big, so this is the correct answer. I suppose the next question then that comes, will the trapezium rule always give an overestimate? Because the shape of the curve, and if the curve was actually shaped that way, then all of the trapezia are going to be underestimates. And then your point, if the curve was something like that, some would be overestimates, some would be underestimates, and I couldn't tell how they balance, and as a matter of fact, they might totally balance. And in that situation, the 26 could actually be the perfect answer. But it's the shape of the curve. Now, that kind of a question is a question on understanding. I reckon if all we do is say to students, here's the trapezoidal rule formula, you use it for finding area under wobbly shapes, give them 20 of them to practice, there's no way they can answer a question based on understanding like that. And I think that's why we have to work on improving the level of understanding so that they can deal with those kinds of problems. Are we okay? And that now brings us to the next section, which is the introduction to integration. And as I said at the introduction to the day, I accept it's higher level Leave Insert material, but I'm asking everybody to hang in with it, engage with it. I think there's a lot for us to learn as junior cert teachers, and it might just influence the way we would teach certain topics at junior cert. Taking into account that I'm saying we should always access prior knowledge, the prior knowledge is going to be, for integration, differentiation. So we'll go through this in 3 sections. We're going to look at antiderivatives, calculating area, and then we're going to look at area as a tool for solving problems. And with prior knowledge being differentiation, if you check through any of our teaching and learning plans, that is always the first section in the teaching and learning plan. And on your desk you've got a 104-page teaching and learning plan on the introduction to calculus, on the introduction to integration. Here's the syllabus, and there's a couple of interesting points for the people who actually teach this. First of all, the first sentence, recognise integration as the reverse process of differentiation. Now, that was something that I might have said to my classes in the past, one sentence at the beginning of the lesson, and they never again mentioned it or bothered with it. Now it's a specific learning outcome in the syllabus, so I think it has to get more attention because clearly it can be assessed now. Use integration to find average value. For those who have taught higher level Leave Insert, that's a new little element on the syllabus, so we try and get a look at that towards the end of the session. And then these are the functions that our students have to be able to integrate. Now what I mean by that is they are the functions that our students have to have a technique to integrate. However, they may be asked to integrate functions that they do not have a technique for integrating. Now I know that sounds really strange, but if you can kind of hang with me for 45 minutes, you'll see where that's actually going. But it is an important point. These are the functions that they must have the techniques for integrating, but they could be asked to integrate functions that they do not have a technique for integrating. We'll just see where it goes. Prior knowledge is differentiation. So in the workbook, we're going to get our students, and I'm treating you now like 60 or higher level students, we're going to do a little bit of prior knowledge from the workbook on page 4. Down the left hand side you have a list of functions, and on the right hand side you're asked to write down the derivative of each of those functions. So in your groups there, page 4, write down the derivative of each of those functions. What's the instantaneous rate of change of 5x minus 10? What's the slope of the tangent to the curve x squared minus pi? What's the derivative of x? What's the rate of change of sine x? What's the slope of the tangent to sine x minus a third? Derivative of sine x plus 9. I keep shouting. Great. What's the instantaneous rate of change of a half x squared? And what's the derivative of a half x squared minus that number there? X again. Now, a couple of things there. Notice the way I ask the questions. there's a lot of revision going on there, because you have the straightforward technique of differentiating, but equally well, in the way I ask the questions, we're doing the revision of what are the applications of differentiation for our students. And I think that's something that we need to be careful of in our classes. The word it, and the word next, and the word answer. What's it? What is it? You know, okay, by the time you have 5 of those done, we all know what it means. But if you start saying, what's it, what's it, what's it, next, 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 what's happening? Students have given up thinking, they're doing rote, they really don't know what they're doing. So we constantly need to reinforce, we're doing the derivative, the application of this is instantaneous rate of change, its slope of the tangent. And I don't care whether I'm doing integration at Leaving Cert level or I'm doing patterns at first year. Like that kind of thing, I think we need to think about reviewing. That the thing becomes so rote, all they're doing is copying down, they're almost doing a pattern in their head. They go home to do a bit of homework tonight, but it's 7 hours later when they go doing it, and they're out of the rhythm, and what's happening? So I think that kind of approach we certainly need to take. Now, what I'd like to ask you is, do you notice anything happening there with your answers?
Some of them are.
Some of them are, so you're telling me some functions have the same derivative. Explain to me, how come some derivatives have the same derivative? Because of the constant. Now, I'd venture to say, with the old syllabus, I'd be delighted with what you have said. She knows what she's talking about, and I'm happy. But now I'm thinking they're going to be asked on exam questions, explain your answer. And I'm not too sure that because of the constant is a great explanation. Would they get full marks for it? Does she really fully understand? So I'd be trying to refine that explanation from people and get them to kind of, what do you mean by because of the constant? Can I take one step back first? Because some people don't think of it in terms of the scaling and shifting, and they're not wrong. What they say is, well, a constant by its nature has, so it has no rate of change. So the constant contributes nothing to the rate of change. So the constant contributes nothing to the derivative, to the slope of the tangent. And that's one explanation, but I think I prefer your one because to me it's visual. Let's see, can I find the right GeoGebra file this time? What is the derivative? The slope of the, so look, there's the function on the left and there's the tangent. What's the derivative? The slope of the tangent. If I put all the slopes of all the tangents together, what do I really get? What we called in workshop 8, the slope function, the derivative, and there it is over on the graphics 2 screen. And the way it looks here, the derivative of a cubic is a quadratic, and we kind of discussed that in workshop 8. But now, what you're saying, what's the difference between that and that function plus 6 or plus 5 or plus 3? It's only the same function. Doesn't matter whether it is a line or not. It's only the same function shifted vertically. So if I say the shift is 8, what will the function look like? Exactly the same, only 8 units up. Who's supposed to know that? Junior certs. On condition that the junior cert teachers have interacted with scaling and shifting and got that whole idea of intercept on the y-axis, parallel curves. There's nothing here that's higher level Leaving Cert. This is junior cert. So the junior cert teacher, if you like, needs to interact with that scaling and shifting in such a way that it makes the understanding easier here. So now, what's the slope of the tangent to the blue curve, to the shifted function, it's the very same. And how many of them could there be? Infinite. So, what are we saying really? So, there's an infinite number of vertically shifted functions, all of which have the same slope, all of which have the same rate of change, all of which have the same derivative. Okay, let's reverse the procedure, because in maths we do tend to look at the reverse. As soon as we look at something, we slap it into reverse. What's addition? What comes next? Subtraction. We did multiplication, what came next? When we did squaring, what came next? Square root. When we did sine, what came next? Sine inverse. So like, it's a kind of a natural thing to look for the, let's go on reverse. So if I told you that the derivative of some function was 5, what was it before it got differentiated? We've kind of just done it. It could have been 5x, but there's actually an infinite number of vertically shifted functions that it could be. What would they all look like? 5x plus r something, some constant. So how could we write it down in general? So explain to me what this is. It's a function, great, to begin with. So, and it doesn't even, it's a linear function in this case, but it doesn't have to be. But is it a function? What did you tell me about that C earlier on? It could have an infinite set of values. So that isn't one function, that's an infinite set of functions. What do they all look like? Parallel, or if you like, vertical, shifts of each other. Now keep that in mind. This is an infinite set of vertically shifted functions. If we do differentiation going one way, what do we call it going the other? Just to get the terminology right. And what we call it is anti-differentiation. It's anti-differentiation is what we call it when we reverse the differentiation procedure. And the notation for it is that if the function is called g of x, the antiderivative function is called uppercase g of x. That's the international standard for that. So it's uppercase g of x. If you call the function f of x, the antiderivative is uppercase f of x. If you call it h of x, the antiderivative is uppercase h of x. That is the convention. Now, the next activity, it's not in the workbook, it is in the teaching and learning plan though. And what we have is a whole series of functions that I'm now going to ask the students to find the antiderivative of. The first one is actually done for them, although there's a misprint in it. It's find the antiderivative of 7, and it's capital F of x equals 7x plus c. It's correct on the board, but in the teaching and learning plan on page 70, it's actually incorrect. It should be find the antiderivative of 7 on the left-hand side. Do you see that? So the antiderivative of 7 is got for them. It's 7x plus c. They're also asked to find the antiderivative of minus 11 of x squared, of x cubed, of x to the power of 4, of x to the power of 5, as many of them as you like. Now listen to what you're asking your students to do. We've explained to them what antiderivative is. Have we given them any antiderivative techniques, or rules, or methods? We haven't. Yet, we're asking them to find the antiderivative of these things. Now, they're my 6th-year students. This is their halfway through their first lesson, or maybe it's the end of their first lesson. So, what are they going to do? Let's pick one of them. Let's just pick, we'll say, the x squared one. And let's try and find the antiderivative of x squared with the level of knowledge that the students have at this point. And as a kind of an aside on that, I'm just going to say, one of the things that I think Project Maths gave me that is very, very valuable, actually the most valuable thing they gave me, was that. Do you remember those posters you got, the problem-solving posters that you got back at one of the earlier workshops? I think that's very important, because what first, second, third year teachers should be doing, I think, from the very beginning is getting their students thinking about problem-solving strategies. I know in the past what I did was I gave my students maths techniques and then I gave them a problem. Give them 5 minutes to do it, and at the end of the 5 minutes, well, what's your answer? I don't know. But what's your problem like? Why can't you do it? I don't know. And they're there sucking biros, hoping that divine inspiration is going to come up out of them. And you know, if you do nothing, nothing happens. But once I got the posters, and I was lucky I had my own classroom, I put the poster up on the wall, and starting at first year, I started, every problem we do, what's your problem-solving technique? No, we went through them, draw a diagram, trial and improvement, look for a pattern, work backwards, all the various things. But then you never attempt a problem without saying what strategy you're going to do. And at least if they said, well, I'm going to spot a pattern, well, then will you write down the pattern? Or I'm going to work backwards. Well, because they knew what they were going to do, they stopped sucking the biros and they actually started using them. Now, you're not saying they always wrote correct stuff, but now they're doing something. And if they're actually working, they're going to begin to be able to refine it. They'll begin to learn when each strategy is best. They'll learn to see when it's gone wrong. And by the time they get to 5th and 6th year, problem solving is much less of an issue for them if they've been through that. And that's one of the things that I think is very valuable that junior cert teachers have to contribute to us. So I'd be saying to my students here, okay, I'm trying to get you to get the antiderivative of x squared. Which of those strategies are you going to use? Now, considering you know very little, lads. So what do you think is kind of the obvious one? Working backwards or trial and error? Yeah. Can I take the lesser of those for a second? Trial and error. So just have a guess, chance something. And I took this into a class and trialed it out, and a lot of them did trial and error, and the answer they gave me was 2x. That the antiderivative for that was 2x. And the antiderivative for that is 2x. If, how would I check it? How would I check if that is the antiderivative for that? What should happen? So, if I differentiate that, I should get both. Bad guess, we better try something else, lads. Maybe let them have 1 or 2 more guesses, but of course, if they're not guessing right fairly quickly, I need to give them a prompt. And of course, the prompt would be, what are you doing anyway, lads? What is anti-differentiation? The reverse process of differentiation. How do you do differentiation? You lower the power by, so damn it, if you're doing the opposite process, what should you do? Now, the student who tried the work backwards procedure first would probably come to this without that. Is this correct? Yes, it is. If, when I differentiate it, I get x squared. Do I? What's wrong with my answer? Now, again, the 3, fair enough, but that 3 doesn't say a whole pile to me. Not great communication, if you like. What do you mean by the 3? What's the 3 doing to the x squared? It's multiplying it. So what's it doing? It's making it 3 times too big. So what should we have started with? Something which is 3 times smaller. Is that the right antiderivative for x squared? Is that the perfect antiderivative for 3x squared? Sorry, is that the perfect antiderivative for x squared? It's not, because as you say, there's an infinite family of vertically shifted functions, all of which would give x squared. What do they look like? How do you get a shift? Constant. So actually, what is the perfect antiderivative of x squared? Yes, it's a third x cubed, but there isn't one answer. There's an infinite number of answers. What do they all look like? Parallel to third x squared, or if you like, third x squared vertically shifted. Now, if we have that done with all of those, we're actually going to have a table of values. They'll have worked through it, and for minus 11x, for minus 11, they will have got minus 11x plus c is the antiderivative. For x, they will have got the antiderivative is a half x squared plus c. For x squared, the one I modelled with you, they'll have got a third x cubed plus c, and so on. Now, if my junior cert teachers haven't let me down, what's the kind of logical thing to do if you have a table of values? See if you could have a pattern. And if junior cert teachers have been interacting with that all the way up, this will just happen automatically at this level. So let's see if we can see a pattern. What would the antiderivative of x to the n actually be? Well, look for the pattern. X to the, there'll be a 1 on. And don't forget the family of infinite family of vertically shifted functions. I'm saying that rather than don't forget the c, because to me, don't forget the c means nothing. Whereas they're actually, you're having an interpretation of what's going on if I start to say, and don't forget the infinite family of vertically shifted functions. So what have we done? We have actually derived the rule. They've come up with it themselves. Some people will say to me, Tony, wouldn't you just give them the rule and spare time? Now, there is a point to that. But that activity, working through that activity, what is it driving home? It's driving home the fact that antiderivative is the reverse process of differentiation. And remember, that was the first learning outcome on the syllabus. It's no longer just a sentence I can say. They need to interact with it. They need to relate to it so that they are aware of what they're actually doing. A little bit of terminology. This is the indefinite antiderivative. It's called the indefinite antiderivative. What is it? It's the infinite family of vertically shifted functions, all of which, when you differentiate them, would give whatever, x to the n in this case. Now, with that much done, I have an activity for you on page 5. But before I let you loose on it, can I ask a question? Your 5th, 6th year students that I'm teaching, this is the first time you've seen or heard this, you're not teachers. Did you hear the word integration? Do you know anything about integration? No. All right? So when you're answering this, You answer it only with the knowledge you're bringing from Junior Cert plus what I have just taught you. That's your prior knowledge to do activity on page 5. So if you wouldn't mind working through that in your groups there, and we see how we get on with it. First question, what's different about this over the ones we did previously? And I think everybody nailed it. You have an extra piece of information. You're given a point that you... Now, the idea here is like that you want your students to sort of realise, well, if I'm given an extra piece of information, then surely that's going to have a knock-on effect somewhere. Like, what's going to be the effect of this extra piece of information? Next question was, write down the antiderivative of f of x equals 3. And I'm going to be a small little bit pedantic with you now. F of x equals 3. What is the antiderivative for that? Yeah, because the antiderivative of a function is a function. So it should have a name. So really, you need to be naming it. And then what? We all got the 3x plus c. Next question. Draw the graph of that with c values going from -3 to +3 in increments of 1. What are you drawing? Now the question is, what's that? Haven't we dealt with it? What is that? It's an infinite set of vertically shifted functions, all of which, well, sorry, it isn't infinite this time though, is it? Because we're only going to put in values from, so it's 7 functions. What kind of a function is it? So, if the first one is f of x is 3x minus 3, what does it look like? What is that, the graph of? By the way, what could I put in instead of f of x? So we're really talking about y equals 3x minus 3. What's that? Who knows that that's a straight line? What students should know? Junior certs. That's junior cert work. How do you draw it? What's the quickest way of getting it drawn? Is -3, which is a rise of 3 gives a run of, bang, there it is. And what about all the rest of them? They're just vertical shifts, they're just parallel. What's the only thing that'll change? The intercept, and it'll become -2, -1, not. I got a bit excited with this, lads. I actually started at -7 and went to +7. I just love my maths so much. But there it is. Now, next bit, which one goes through 1, 5? And as I was saying down there, this is a bit like the joke, find x. You know, all you want to say is, there it is. Look, it's that one. If you do need the equation of it, do you have to do algebra? Not saying the algebra is wrong, but can you just look at that and read the equation of it? And it's f of x equals 3x, and it crosses at 2, so it's f of x equals 3x plus 2. That activity that I've just given you, who could do it? Junior cert students? There's one bit you'd have to leave out. Find the antiderivative of. But could you give junior cert students a function f of x equals 3x plus c, ask them to draw that for different values of c, ask them to identify the one that goes through 1, 5, ask them to name the equation of that one. If you did give them that activity in junior cert, would you be covering or revising the junior cert syllabus? Definitely. And what are you doing? You have a leaving cert activity, an honours leaving cert activity almost done. It's just we need to take it one step further for the integration. Now if I'm doing that down at junior cert, look how that's speeding up what the leaving cert teachers and students have to do. If these students are very familiar with scaling and shifting and intercept on the y-axis and all that sort of stuff, this becomes a very short and a very easy activity and approach into integration. If they haven't interacted with that down at junior cert, you're going to have one very frustrated teacher anyway, because the thing is going to take ages, and it shouldn't, because all of this really should be prior knowledge. So now, what was the effect of that extra piece of information? So instead of having the entire family, it identified specific member or members of the family. I'm not married and I don't have a family, but the kind of the original situation, the indefinite antiderivative, it's almost like saying Tony's going to marry one of the Murphys. Do you know, like, but it could be any one of them. But then, what did the extra piece of information do? It is the blend. You know, it specifies it, it ties it down. So that's the difference between the indefinite antiderivative, which is the entire family, and the distinct, which is the specific one, the blend, or the foxy one, or the whatever. That extra piece of information, physics students might be used to the terminology. It's the initial condition is what it's referred to as. Now, here's actually this is on the current sample paper. And the question is, write down 3 distinct antiderivatives of the function g of x equals x cubed minus 3x squared plus 3. So they're asked to write down 3 distinct antiderivatives of that. Tell me what to write. Capital G of x, right, equals minus, and we can do the tidy up after if we want to. Go on. No, that's the thing. I suppose us as teachers, from the way we used to do it, would have a tendency to stick in the plus. See there. But look at the question. It's looking for the distinct antiderivatives. So it's looking for the blonde, the redhead, and the baldy one. So you're sticking in a specific value, a +1, or a -4, or a plus pi. Would it be all right to stick in pi? Sure, it is only a number. Would it be all right to stick in 0.74936? And I've started doing that in my teaching, because now looking at the questions they're getting very awkward numbers, and so I want to get them used to not just seeing everything nice. Teacher yesterday said to me, Tony, don't put in any constant. Just leave it at g of x equals x to the 4/4 minus 3x cubed on 3 plus 3x, and leave it like that. Would that be correct? Yeah, that's a constant of. It's still a specific one member of the family, so that would actually be correct. Another thing, someone lately said to me, what's all this g of x crack? A function is f of x. You can't be going around calling functions g of x and h of x and k of x, like, can you? And sure, you can call them what you like. But at junior cert level, a lot of the time, we do tend to just constantly use f of x, f of x, f of x, f of x all the time. And then our students suddenly see a h of x and they don't know what to do with it. They don't even realise it's the same thing. So at junior cert level, where we're introducing our students to functions to begin with, should we get into the habit of naming them anything under the sun? And I've actually started going, look, if I'm talking about profit, I'll call it p of x. If I'm talking about velocity, I'll call it v of x. And actually let it mean something as well. Because it's small things like that that can throw our students sometimes. Explain what is meant by the indefinite antiderivative of the function f. Now think about it, and think about what we've been saying for the last half an hour. Indefinite. What's the indefinite? It's the family, it's the set. So it's the infinite set of vertically shifted functions, if you want to, all of which, when you differentiate them, would give f. Now, that question on an exam paper, if all you do is give them the rule for integration or for this technique for antiderivative, there's no way they can answer that question. So we kind of had to go through the idea of the shifted functions and the reverse process. Otherwise, that question doesn't really mean anything to a student. And finally, write down the indefinite antiderivative of the function g. What's the indefinite? We just said it. It's the entire. So what are we writing down? That thing up there with the plus c.
You have to define what c means then.
Sorry?
You have to write down c's x between.
I suppose theoretically we should be saying c is an element of, or isn't it? Because it could be any real number. So to be complete, we should put that in, yes. Are we all right? So look, we've looked at antiderivative as the reverse process of differentiation. We've got the indefinite antiderivative is the set of all possible antiderivatives. It's the infinite set of vertically shifted functions. And then the distinct antiderivative is the one, the specific. It's one element of the set which actually satisfies the initial condition. So that's kind of what we've done at this stage. Now I hope I finish that on a Friday. And we'll all go home and we'll have a nice relaxing weekend, and we're back in Monday morning and we're starting this new section. We're going to be calculating area. Totally new section. Nothing to do with antiderivative. That's a photograph of the leisure centre in Ballymun. Project Matt's office is based in Drumcondra, and when I go into work in the morning, I pass by the leisure centre in Ballymun every morning. And of course, being the kind of individual I am, I'd be thinking about maths, and I was kind of looking at it one day and I said to myself, if I was the window cleaner there, how much glass would I have to clean? So, question is, what's the area of glass on the front of the leisure centre in Ballymun? Talk to me about it. What is the area glass in the front of the leisure centre in Ballymun? And I went back to the PowerPoint, not the Geogebra. Talk to me. Can you find it? How will you find it? Have we done anything like this today?
Yes.
What? Yeah, because what about the roof of the leisure centre? It's curved. So what have you there really? An irregular curve shaped area. So talk to me about it. All you can do is get an estimate, and the tool for getting the estimate is trapezoidal rule or trapezium rule. Now, what I need to do, so if the trapezium rule, like how did the trapezium rule work? Really, you had a function and you found the area underneath it. That's more or less what you were doing, really. You had a shape, you're finding the area underneath it. So I'm going to try and get a function to model the roof. Now, you don't have to worry about that. But what I did in Geogebra, well, what somebody did for me, was put the picture into Geogebra, banged in a whole load of points all along the roof, about 40 of them, and then used a command in Geogebra that says fit function. And it just drew the function that would fit that. We don't have to worry about that because we'll always be given the function, or we'll be given information to be able to get the function. But there it is. So now that's the question is find the area underneath that function. We were given the question in a real world context, find the amount of glass in Ballymun Leisure Centre. We've actually turned it into, we've taken the context out of it. It's find the area underneath that function. So look, I'll take the context out of it completely. Let's fade out the photograph because there's any bothering me. And You know we can only get an approximate, so everybody thinks, oh well, this is the trapezoidal rule, and of course you could do it that way. But I have a problem now. I know what's coming. I'm the teacher and I know what's coming. And to be honest about it, the maths that's coming is really, really difficult if I use trapeziums. So I'm going to go back to using rectangles. Now, you could have a rebellion on your hands in class with that, because you're saying, God, we spent saying trapeziums were the best. But we also spoke about efficiency and effectiveness and simplicity. And some student actually said to me, sure, you can use any shape you like, so long as you use enough of them. So because we had that discussion, there shouldn't be a major issue about saying, look guys, to keep the maths a bit easier here, we're going to revert to rectangles. And so long as we take enough of them, we'll get just as good an approximation. Now, I mightn't have made such an issue if I was teaching an ordinary level class, because this wouldn't be coming. But teaching my honours class, knowing that with this was coming down the road, when I was doing the trapezoidal rule, I was aware of, don't have a rebellion here, get the teaching done. So we're going to use rectangles, and sure, I suppose the simplest thing to do is use one rectangle to find an approximation for the area there. And how would you work out the area of a rectangle? Height by width, and look, I have values in there. But let's suppose you didn't know the values. What's the height? Tell me the height another way. Well, okay, let's say I didn't even have a scale on it. What is the height? You said it to me when we were doing the trapezoidal rule. It's a y value. What y value is it? First y value. So what is it? All right, but no, there is another way you could write down y1. Couldn't you always call it f of x1? It's the y value going with the first x value. And what do we multiply that by? The width. Are we all happy? But that's only an approximate. So really what I should be saying is the approximate area is that. How would I improve the approximation? Increase the number of rectangles. Okay, let's increase the number of rectangles. Now we've 2. In general, what would that area now be? How would I write it down? First rectangle plus, and what's the height of the second rectangle? Can we just look at the widths a second? Of course, the width now is smaller than it was originally, isn't it? The width now only goes from 0 to 8, or if you like, it goes from 8 to 16. So what's the width? It's really the change in the x value, isn't it? 0 to 8 units, or 8 to 16, 8 units. What's the maths way of writing down the change in x? That's one way, x2 minus x1. There is another notation, delta x. So I could replace that with delta x, which they should have seen in the introduction to differentiation. Do you remember workshop 8 when we were doing the Angry Birds GeoGebra file? The delta x came in there. So it should be prior knowledge. How will I improve my estimation? More rectangles. And we could do a Jordan job on it and have more and more and more and more. How will we write that down? Oh my God. Because it will now be f of x by delta x plus f of x4 by delta x. And that will go on and on and on and on. And how many have we? I don't know. We have. Now, can you stop there a second? That looks awful on the board, but what is it? What's f of x1 or what's any of those f things? They're simply heights. What's this? Widths. So what are you doing there? Height by width. So what's any one of those? Area of a rectangle. What's all of them? It's just adding loads of rectangles. Markers are awful expensive, lads, so I'd hate to be writing that out too often. So is there a shorthand notation I could use for adding up all of that stuff? The sigma notation. What students know the sigma notation? And I'm going to answer my own question. I think junior cert should. What's the mean? The average. There's a formula for the mean in the tables book. It uses the symbol sigma. Surely if there's a formula in the book and you're encouraging them to use it, you'll explain in the notation. So again, if the junior cert teachers have all that sort of stuff done, we're flying here because they're used to this notation. What? Some height by width, the height starting at the first one, going on to the nth one. Now again, that's a funny looking notation and it could frighten people. But what's it really saying? Height by width. So, area of rectangle, add up the area, loads of rectangles. Now, if you wanted your answer to be like me, perfect, what would you do? Well, okay, but I suppose from a point of view of your rectangles, to get a perfect answer, how many rectangles are you going to use? An infinite number. So let's use an infinite number. And I'm sorry to say, your percentage error is 100%. You couldn't be more wrong. What is after happening? Why is she 100% wrong? You have an infinite number of rectangles. You have an infinite number of rectangles. What's the area, the width of every one of them? If you have an infinite number of them? 0. Which means what? Everything has been multiplied by big fat 0. So, whoops. I'd love to have an infinite number of rectangles, but I can't because it gives rubbish. Did we come across that situation before, where we'd love to have infinite, it gave funny maths? Did we find a way around it? And we did. Yeah? Limits. Instead of having an infinite number of rectangles, look what happens as it approaches infinity, the idea of a limit. And that's on the ordinary level Leave Cert syllabus, and it's on the higher level Leave Cert syllabus. And you certainly did it in workshop 8 when we were doing the first principles differentiation. So look, there's the limit as n tends to infinity. And what does it give you? Sorry, the colour is not great, but the error is 0%. It's perfect. So what do I have to do this to make it be the perfect area? Just put, as the number of rectangles tends to infinity. Now, if you wanted, you could have delta x tending to, if the number of rectangles tends to infinity, what's happening to the width of each rectangle? That's tending to, so you could have either down there. Is that line on the board wrong? Spot the deliberate mistake. It's not an approximate anymore, because once you put the limit in it, it's actually perfect. So we've gone one step higher now than the ordinary level syllabus, because what can the ordinary level students do with irregular curved areas? They can only get estimates, they can only get approximates. What can we do? We can get the perfect area. Now again, look at this. Notation looks very difficult. Break it down. Height, width, area of a rectangle, adding all the rectangles together, and you're looking at what happens as the number of rectangles just gets jodolin more and more and more and more, going to infinity. Again, markers are expensive, and that's a lot of writing. So there's a notation for that. We use an elongated S instead of all of that. S for the word, sum, because that's what you're doing. And the heights are just f of x. And can anyone tell me what is delta x when it gets really, 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 really small? What's the notation for delta x when it gets really, 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 really small? That's what dx is. That's what dx is. And what's dy? It's delta y getting smaller and smaller and smaller. So look, there's a word for that. What's it called? Integration. But hold on a second now. If you like, last week we did anti-differentiation. This week, what have we done? We found area underneath a curve. And at this point in time, is there any link between those? No. I didn't mention antiderivative since I went to Ballymun. So at the present point, we're at a stage where we have two things. We have antiderivative, we have integration, which is finding area underneath a curve, and sort of there's a big chasm between them. I don't think there's any link, or is there? Just one last thing, talking about songs and so on. Julio Iglesias had a song called Begin the Beginning. But you don't always have to begin at the beginning. Because if there was 3 window cleaners, I might only be responsible for the bit inside, so I might only be starting kind of in there somewhere, and I might only be finishing in there someplace. So I need to introduce into my notation a way of saying where I'm really beginning and where I'm really ending. And the standard for that is we put the beginning down there and we put the ending up there. So now what is this saying? Read that. And I personally would never read it as the integral of, because that means nothing to me. I would read it as find the area underneath the function or underneath the curve f of x and the x-axis between a and b. And it actually means something to me now. With that in mind, there's an activity on page 7 of the workbook that I'd like you to work through. There's an activity on page 7. Now remember, you only have the level of knowledge that we're working with here. Have a go at that Blackboard activity on page 7 with that level of knowledge.